Welcome to EDU World Space.
So in this question, we have a spherical pressure vessel, right? And this vessel has an inner diameter of 2 m and a thickness of 10 mm, right? Now a strain gauge having a length of 20 mm is attached to it, right? And it is observed to increase in length, right, by 0.012 mm, right? Now, when the vessel is pressurized, now what we are required to do over here is that we need to determine the pressure, right? The pressure that is causing this deformation, and we need to find out the maximum in plane shear stress, right? And absolute maximum shear stress, right? Absolute maximum shear stress, right? So the material is steel, right? The material is steel and its elasticity is equal to 200 gigapascals, and the epsilon is equal to zero point 0.3, right? So let's start with the solution. Now, as you can see over here, it's a very easy one, but it's a little bit lengthy. So, um, recall your previous knowledge from chapter number 8, right? Because we would be needing it to solve such type of questions, right? So, in chapter number 8, it deals with thin pressured vessels, right? So, and in order to use equations from chapter number 8, that is 8.1 and 8.2, right, the ratio of the radius to the thickness, it must be at least equal to or greater than 10, right? So in our case, let's check that whether it's greater than 10 or not, right? So the radius is 1, and over here we have 10 to 10 raised to power 3, that is equal to 100, and 100 is absolutely greater than 10, right? So it means that we can invoke the equations included in chapter number 8. Now, the part of chapter number 8 that describes the given object is that of a spherical vessel, and therefore equation 8.3 will come in handy, right? So equation 8.3 will come in handy for finding the pressure. So the equation is that sigma sub 2 is equal to P times R divided by 2T, right? Now here P is not the parameter but the gauge pressure, so meaning it is what we want to find. So in order to find P, we need to rearrange it, right? So P is equal to 2 times T del 2, sigma sub 2 divided by sigma sub 2 divided by R, right? So now this equation, right, this equation has two unknowns, the pressure and the plane stress. So reading the limitations part, it shows the object is under pixel, right? And also it shows that the stress is equal to sigma sub 1, that is equal to sigma sub 2 times sigma sub 3, and that is equal to 0. Now, using this in the Hooke's law, we can find a relationship between the stress and the strain, right? So it means that the strain is equal to 1 divided by the elasticity, right? Square bracket, the sigma sub 1, negative the epsilon, parenthesis, sigma sub 2 plus sigma sub 3, right? Now what we're going to do is that instead of sigma sub 1, we will substitute only the stress, and also over here, and this is equal to 0, right? So let's write it like that. So we have 1 divided by E, and over here we have stress negative epsilon, again stress plus 0, right? So now I'm going to simplify it. When I'm going to simplify it, so we'll be left with the stress 1 negative epsilon, right, divided by E. Now this shows that what is true for stresses is also true for strains, right? So it means that from this equation, we conclude that the strain is equal to epsilon sub 2, that is equal to the strain in the x direction, that is equal to the y direction strain, and that is also equal to the strain in the z direction, right? Now recall the elongation equation, right? So that is epsilon is equal to the change in length divided by L, right? And in our case, it's the strain that is equal to del L divided by L, right? Strain gauge length. So that is 0.012 divided by 20, right? And now using this and solving the result for the Hooke's law, right? So we have epsilon equal to stress 1 negative epsilon divided by E, right? So rearranging it, so we have 1 negative epsilon. So from here, what we are going to do is that finally we will substitute this into the equation 8.3, right? The first equation that we wrote, P is equal to 2 times T times the stress divided by R. So just substitute. So we have 2 times T times E times the strain divided by 2 times 1 negative 2 epsilon times R, right? So we have all of these values, right? Just plug them in and you'll get that the pressure is equal to 3.4286. That is approximately equal to 3 point into 10 raised to power 6, right? Pascals. So that is equal to 3.4 gigapascals. And since the stresses will be same everywhere, so it's safe to say that the stress is equal to um, the principal stresses, right? Sigma sub 1, sigma sub 2, because they will be the same everywhere. And this means the principal stresses have the same value, right? And the same sign. So it means that equation 9.13 gives us the absolute maximum shear stress, right? So we have absolute maximum, that is equal to sigma sub 1 divided by 2, and that is strain times E divided by 2 into 1 negative epsilon, right? Again, just plug in the values and we'll get that it is equal to 8.5714 into 10 raised to power 7 pascals, and that is approximately equal to 85.7 megapascals, right? So this concludes our complete solution